All right, our last example before moving on to a new topic entirely, we're going to talk about rockets and rocket propulsion in our next lesson. But before we do that, we're going to look now at what happens to a moving platform when the platform acquires mass. So it's getting heavier. The platform is getting heavier, and what we have to think about is how does that affect the motion of the platform? Well, in the first instance of our consideration, we are looking at adding 4 kilograms of mass. So 2 kilograms of mass, 2 kilograms of mass every 3 seconds. So let's consider putting 2 of these 2 kilograms on there, so 4 kilograms total. And if the 2 kilogram masses are initially moving at 5 meters per second and the platform is moving at 5 meters per second, we get an initial momentum of the 4 kilograms, 2 kilograms times 2, times 5 meters per second forward, plus the platform, 10 kilograms at 5 meters per second forward, for a total of plus 70 kilograms meters per second plus x at moving forward. Well, if we lower those 2 kilogram masses onto the platform, making the platform heavier, but not changing anything with the speeds, then we see that we have the same final momentum, plus 70 kilograms meters per second in the positive x direction, in which case we had no change in momentum. So platforms that acquire mass already moving at the speed of the platform need no additional force to keep the platform moving at 5 meters per second. So do not think that just getting heavier, just getting more mass, necessarily means you are slowing down. If you are acquiring that additional mass already at the speed you are moving, you will just continue moving at that speed. But, on the other hand, what if the mass you are acquiring is not moving at the speed you are moving? So what if you are acquiring mass that is moving at 1 meter per second and the platform is moving at 5 meters per second, and then after the mass lands on the platform, we want the entire system to move at 5 meters per second. Well, in that case, we do have a problem, because the initial momentum of those two kilogram pieces was only 1, and we needed to get them to 5. So the initial momentum of the system is now 54 kilograms meters per second, because the 2 kilogram pieces didn't have enough momentum. The final momentum of the system is still the 70 kilograms meters per second, because we're going to have them move at 5 once they land. But that means we do need an external force pulling the platform forward once it acquires those slower moving pieces, based on this external force representing the change in momentum as a function of time. Now notice the change in momentum only affects the 2 kilogram pieces. We don't need to do anything with the platform. The platform is already moving at 5. It'll continue moving at 5, no additional force needed. But the 2 kilogram pieces, right, at 2 kilograms every 3 seconds, and the velocity of those 2 kilogram pieces is going to go from an initial speed of 1 to a final speed of 5, will require a force pulling the platform forward at 2.67 newtons based on the fact that it is acquiring mass that is moving at a slower speed. So this problem I know is a little bit tricky in terms of wrapping your mind around, but I think if you think about mass that's not moving at the speed you want it to move at, you have to do something to get it moving at that speed. Now, the rearranging the equation and associating the m with the delta t gives kilograms per second. So that's kind of neat and convenient to think about in terms of if you're given a rate at which mass is being put onto a platform, that will be your kilograms and seconds. And then we just need to see how much the platform speed is going to be changed by. So, again, make sure you have all of your annotations down on this page. Let me erase all of my little commentary circles and checks so that you get all of the annotations that you need down here. You can pause it if you wish. And this is our last example. We are going to move on to rockets and rocket science and see how conservation of momentum applies to a rocket system.